Okay, so good morning. Welcome to the Grasland Thursdays. Grasland Thursday is a series of webinars we organize every Thursday at 10 on various HPC topics, such as this one today on Rust language, which will be presented by Hadrien from EGC Lab. But first, let me give you a little presentation of the organization team. There is Pierre Aubert, a research engineer from the LAP, a French laboratory of physics and particles in Annecy, the French mountains, with the creator of the Grasland School. And Karim Azoum and I from Terratech, within the French NCC called CCFR, and with the LAP of Annecy, we co-organize the Grasland Thursdays and the Grasland School. Because those 17 Grasland Thursdays you will discover are held by 9 incredible teachers who will each one of them give you webinars on their topics, introducing at the same time the program of the summer school. So what is Grasland School? It's a free summer school dedicated on programming and optimization on heterogeneous architecture. Created 2 years ago by Pierre Aubert with a few people in Annecy. The French NCC joined him last year to help him develop it not only in Annecy, but also in 12 satellite sites among 4 countries. Those satellite sites helped us reach more people by broadcasting the school live in their locations. The summer school had a 2-week program, 1 week on CPU and 1 on GPU. But everybody was free to choose the courses they wanted to attend thanks to our à la carte option. We finally trained over 500 people, and everything is available still on replays on our website and YouTube channel. So you can access it if you want, but everything was in French. This year we are going European, so all will be in English like this webinar. You have various ways to attend the school, as you'll see in the video I'm going to launch for you. And also we invite you to be part of the team and become a satellite site yourself if you want to host the school. We are able to provide you everything, all courses, containers, access to the teachers, and also to connect you with our growing HPC community. So now let me play the video for you.
Do you sometimes feel limited by your resources or unsure how to maximize the potential of your HPC resources? Imagine a place where collaboration, creativity, and learning converge with high-performance computing. Welcome to Grasland School 2025, Europe's leading summer school for HPC. Taking place from June 23rd to July 4th. Over 2 weeks, students, academics, and industry professionals from across Europe will explore the frontiers of programming while building a vibrant community. Together, we'll discuss programming and optimization on heterogeneous architectures, highlighting their respective characteristics and limitations. You'll have a unique opportunity to explore generic optimization methods, as well as the latest technologies and languages for achieving optimal performance. The school is free and open to everyone, and you can participate in person in Annecy, France, with the teachers, at one of our satellite sites in Europe, or online via our live streaming. You can choose from an intensive program or à la carte courses to develop your skills at your own pace. With the first week dedicated on CPU and the second on GPU architectures, you will study computational accuracy, vectorization, parallelization, compilation, memory profiling, unit testing, and the various programming languages C++, Fortran, Rust, Python, and Julia. In addition, we will study the MPI, OpenSHMEM, OpenMP, TBB, EVE, Kiwaku, Sycl, Thirst, CUDA, OpenACC, Vulkan, NumPy, Number, QPy, CU-numeric, JAX libraries, and Legit, as well as computation with PyTorch and TensorFlow, and the G++, Clang++, NVC++, NV Fortran, G Fortran, and DPC++ compilers. Throughout the course, you'll discover and use profiling tools such as Valgrind, Perf, Macau, Ensight, Malt, and NumaProf. Each session leads to a practical challenge, the simulation of Gray-Scott's diffusion reaction, which tries to describe how a chemical reaction evolves over time. Simple to understand, but complex enough to push the limits of optimization. Thanks to our specially designed Docker containers, you'll have access to a complete working environment to follow courses and exercises on your laptop or supercalculator. Throughout the program, you'll be guided by a dozen expert instructors, leaders in the field of programming and HPC. You'll have the opportunity to ask questions and chat with them live on Discord, so you can tailor your learning to your needs. Join our growing community of over 500 users to find answers, exchange ideas, take on challenges together, and build bonds that will last well beyond the program. You can also join the Gray-Scott School European network of satellite sites, not only to attend the courses, but why not become a satellite site yourself and host the school in your location? You just need to provide a room, a contact person, and access to computing resources. We'll provide courses, tools, and Docker containers for a seamless learning experience. Gray-Scott School is free and open to all. It's your chance to master advanced programming and optimization, engage with a growing European HPC network, and push the boundaries of technology and training. You can kickstart your journey now by joining Gray-Scott Thursdays, a free webinar series previewing the school's courses. Don't miss out. Register today to attend, whether in person in Annecy, France, or at one of our satellite sites in Europe, or online via our live streaming. Gray-Scott School 2025, where HPC meets your potential.
Okay, so if you have any question regarding the school, you can ask them in the Q&A section, and Pierre, Aubert, and I will be glad to answer you. Thank you for listening. And now it's time to give the floor to Hadrien Grasland.
So welcome everyone to this webinar. This will actually be the first of a two-part series of webinar about the use of Rust, the Rust programming language for numerical computing. Today, the focus of this webinar will be to make the case of why one would want to use this programming language for computational purposes. And let me start by answering a question to myself, which is, what is my ideal computing language? What are the properties that I ask for in a programming language that I would use to do computations? Because there are so many languages available, right, from statistical specific stuff, financial stuff, Python, the GPU stuff, the VM stuff, and so on. So one first constraint I would set myself is that I prefer, whenever possible, general purpose languages, because it means that I do not need to constantly switch between languages depending on what I am trying to do. And it also means that I do not need to handle communication between various languages in larger application, which is quite complicated. Second, because I'm a performance expert, I like languages that make it easy to achieve good performance. And this will eliminate a number of languages and make, in some cases, it's possible to get to high performances, but you will have to work quite a bit on it, like in the case of Julia. And finally, in my experience, you never know how big a software project is going to get. A well-known quote from Linus Torvalds is back when he shared the news about the Linux kernel was, hey, he's just a project I hacked over a weekend trying to make Unix work on x86. Let's see if you can make something out of it. So I prefer also, whenever possible, to use languages that are equipped with tools that make it easier to manage larger applications and libraries. Things like encapsulation, generics, polymorphism, code generation, a hierarchized module system, for example. And this will eliminate languages which do not focus on these areas very much. In the end, when I consider at least the language that I personally know about, I am really left with two choices. C++ and Rust have many things in common. The normal way to compile them is using ahead-of-time compilation, where you turn your program into a binary that the machine can run right away. Neither mandates the use of garbage collection for memory management, which is good for latency-sensitive applications. They both enforce a rather strict and explicit typing discipline. They both provide you with control, a high degree of control on what your program is doing at the hardware level, advanced metaprogramming facility, which allow you to generate relatively complex code from libraries, for example, and a rich vocabulary of abstraction that are so-called zero cost, which means that the intent is that when you use the abstractions provided by the language, you would not have been able to achieve the same result with a custom abstraction that you implement yourself from C or assembly. And the price to pay for all these desirable characteristics is that these languages are both quite difficult to learn and take a while to master. There are so many things in common. What does Rust do differently? Let's address the elephant in the room first. If you have ever heard about Rust before, what you have most likely heard about is the concept of safety. And safety is impossible to properly define without first defining what is undefined behavior, also known as UB. So the idea of undefined behavior is that there are some things your program should never be doing, and it's to the point where the optimizer of your compiler will assume that you do not do it. Therefore, when the compiler manipulates a program that actually does this thing, it will make some mathematical reasoning based on incorrect assumptions, which will produce unpredictable effects, garbage output. But in this case, the garbage output is your program. The problem is that in C and C++, there is a huge variety of built-in language constructs that can cause undefined behavior. You have arithmetic, overflow of signed integers, bit shifts larger than the number of bits of the integer, computing the negation of the minimal signed integer, casts from float to int where the floating point number is not a valid integer, like nan, for example. You have many undefined behavior associated with arrays, collections, out of boundary access, invalidation of iterators if you use iterators, as Pierre showed last time. You have problems with pointers and references. In the case of pointer, they can be null. You should not try to dereference them or access them via the arrow operator. They can be misaligned, and this is also undefined behavior. It works fine on x86. It crashes your app usually on other architecture, and it can cause all kind of other mayhem because, again, undefined behavior is unpredictable. Your pointer may be invalid. It used to point to a valid memory allocation, but now this memory has been repurposed for other things. And also, one very annoying rule of C and C++ is the so-called strict aliasing rule, which prevents you from accessing memory, a pointer pointing to data of a certain type as if it were data of a different type, which means that basically reinterpret cast in C++ is almost never legal. Then you have the issue of uninitialized memory. The compiler assumes that you are never going to read it, and it's certainly never going to use it for any computational purpose. And this is a problem in C++ as soon as you start thinking about things like destructors, which can run on variables that you have not initialized yet in case some exception happens. You have also infinite loops, which are actually also declared to be undefined behavior in the C++ standard. Thankfully, compilers have some heuristic to determine to say that, okay, maybe some infinite loops are okay because actually they are everywhere in computing. But in some circumstances, you can get garbage like your compiler saying that the last theorem from Fermat is violated. And finally, you have the whole issue of multi-threading, dear to our heart in HPC, which means that access to data that is concurrently being written is also undefined behavior. There are many more, and overall, this means that really undefined behavior is unavoidable in real-world code. And what happens when you have lots of undefined behavior in every C++ program? First, you get security problems. There have been some studies in recent years studying the share of vulnerabilities in C and C++ projects that are caused by so-called memory unsafety, which is basically invalid use of arrays and pointers. And if we account for only this kind of undefined behavior, we already explained 2/3 of the vulnerabilities in all large major software projects written in C and C++. And that's just one kind of undefined behavior. So how does Rust answer this? The basic premise of Rust is that outside of a specific construct called unsafe blocks, the Rust compiler proves the absence of undefined behavior, which is shortened to undefined behavior safety, or safety for short. And this safety is actually further spread in three categories. The compiler proves type safety, which means that the values you manipulate should honor the invariants specified by their type. Like, for example, the Rust string type is defined to be a UTF-8 encoded string. And so type safety means that you will never get a string which does not contain valid UTF-8 in safe code. You have memory safety, which says that whenever you manipulate a reference to some data in memory, you have a guarantee that this reference will point to a valid memory allocation, which contains initialized data. And you have thread safety, which means that you cannot, in safe code, engage in behavior that could lead to the so-called data race, where you have one thread writing to some data in memory and another thread concurrently accessing that data, either reading it or writing it. This turns out to be a good trade-off in practice. Why is it a trade-off? First, we do have those unsafe blocks, which allow us to do dangerous things that can cause undefined behavior, as in C and C++. But we need them. We need them because, unfortunately, the compiler does not know everything. It does not know the runtime parameters of your computations, for example. And therefore, it is not always possible to prove that a valid program will not cause undefined behavior at compile time, because the compiler does not know enough. You may say we can check it at runtime. However, that can become too expensive in terms of performance. So sometimes we will need to have some code which is manually proven to be safe. And that's what unsafe blocks are about. On the other hand, where Rust succeeded is that you can do most of your work without using the unsafe block concept. In fact, there are many Rust libraries that do not contain a single line of unsafe code. All the unsafe is fully contained in the standard library and other libraries that they call into. Because the unsafe keyword is used rarely, even in projects that do use it, it means that it's easy to audit the part of your code that can cause undefined behavior, if there is any, just by grabbing the unsafe keyword through the source code and doing some manual proofs. And there is some work on the way to ease more automated proof at compile time in the future. A second problem in C++ that Rust tries to address is not undefined behavior, but unexpected behavior and incomprehensible compiler errors. In C++, this is caused by the fact that C++ is a very flexible language, which provides you with many different flavors of polymorphism, that is to say, abilities to accept data of different type at a certain point in your program. To achieve polymorphism in C++, you can use implicit conversions, including non-explicit constructors. If you do not declare a unary constructor as explicit, it's an implicit conversion. You have function overloading. You can also use default arguments to achieve a similar effect. You can have a virtual method and class inheritance. You can have templates and specialization. And all these different ways of doing C++ polymorphism interact in a complicated and unpredictable way. Templates in particular, which are about compile time genericity and nowadays the preferred mechanism for polymorphism in C++, are particularly hard to use. And the reason why they are very hard to use is that the compiler performs an extremely small amount of checks on your program. Effectively, writing templated code in C++ feels very much like writing code in a dynamic language like Python and JavaScript, except that the runtime errors of Python and JavaScript are replaced by incomprehensible errors at the time where your generic code is used by other people. Let me illustrate this, the point I've made so far, by giving you an example of a simple C++ program. It's just calling a method from, we are going to imagine that's from a third-party library that computes the median of a vector of a number, or at least it should. And it prints it, and that's it. And now we compile this program, and we get an error message, which is pretty long and not that informative. It keeps saying stuff about operator, double inferior sign. And if you look closely, you will realize that actually this error message is not in your code. It's inside of the code of the library that you're using. So let's look at that library then, and let's see if we can find what the problem is. The first thing is, if you have studied the evolution of C++, you may have heard of C++ concepts, which are precisely about preventing the kind of template instantiation time errors that I'm talking about here. And actually, the problem is this code here is using C++ 20 concept, and yet it still exhibits the same behavior that concepts are supposed to prevent, which means that concepts are ineffective at their advertised goal. And the reason why concepts do not work is that they only perform a unidirectional check. They check that the caller of a function follows the concept. That is to say, they check that I, as a user of a function, can only pass vector or floating point data to the median function. But they do not check that the contract that is set by the concept is actually followed by the function under the hood. That is to say, they do not check that this function only needs t to be a floating point number and nothing else. And if the implementation of the function is not kept in sync with the concept, which is like, expecting that the documentation of function is going to be kept in sync with the functions, we know how that goes, then we will have a problem. The thing that actually directly causes the compiler error is that the author of the function thought it was a good idea to try printing out the vector during debugging and forgot to remove the debug statement later on. And this is illegal in C++. You cannot display vectors of things. You do not have any easy way to do it. You just need to write your loop again and again for this common debugging task, which is a pain. You have another issue actually in this code, which the compiler does not tell you about, which is that you are sorting floating point numbers. Here we are using the standard library sort. So you will only get an incorrect result if the input happens to contain not a number, which is not an ordered value. On the other hand, if you are using a sort from a third-party library, I saw a study passed by a couple of years ago, you are very likely to get undefined behavior. Then, assuming we are computing a median of a vector that has an even number of elements, we must use the midpoint rule, right? Except here it is implemented incorrectly, because in case the input is empty, this is true, it has an even number of elements, but the element number 0 is not defined and the element number 1 is not defined either. So this code has undefined behavior. And finally, there is here something that could be a performance problem in larger code bases, which is that we have written divided by 2 using this sort of literal. And in C++, literals are typed. So this is a double precision number, which means that in order to implement this operation, the compiler must take your float result, if it's a float number, single precision floating point number, turn it into a double precision number, divide in double precision, and finally turn back into single precision. My point here is that the issues of C++ go beyond just safety and undefined behavior. I've been writing C++ code for about 20 years now, and anytime I try to solve any kind of problem in C++, the first code I write is full of these little nice gotchas. And people say use static analyzers. I would like to. I've used as many warnings as I can, but only a tiny fraction of the common issues that C++ code contains is actually detected by compiler warnings, even in the particularly strong configuration. Ultimately, the best tool we have is really manual proofreading, writing lots of tests to eventually narrow down all these issues and get a correct result, hopefully for all inputs, including the ones we've not thought about. How does Rust address this problem? By using a very simplified polymorphism system. There is only one kind of polymorphism in Rust, and it's constrained generics. So we have generics, which are like templates in C++, and we have this notion of traits, which are to some degree similar to C++ 20 concepts. The idea is that a type can implement a trait, which means that it implements some standardized operation like equality, addition, subtraction, for example. And then on the side of generic code, we have something new with respect to C++, which is that generic code must tell in its API what operations, what traits it requires from the types. Like I cannot say that I write code that is generic for any type T and then proceed to use the addition operator without a warning. I must say I need a type T that has an addition operator, and the compiler will check for this. And this means that now, unlike with C++ concept, we have bidirectional checking. We check that the user of generic code passes the right type, but we also check that the generic code specifies in its API contract all the properties that it needs from the input type. And as a result, Rust is a much more predictable language. We do not get interaction between many different kinds of polymorphism. We do not get generics with an incomplete API contract because they don't compile, so people figure it out very quickly. And when someone passes in an invalid parameter to a generic function, it gets caught at the highest level entry point, not deep inside of the implementation of the library, as is common in C++, which means that invalid use of generics is much easier to diagnose and understand. Let's illustrate this by literally translating my previous code to Rust and see what happens. So the compiler this time reports only 3 different errors, which, as you can see, are much more concise. The first error, something went wrong here, is that we cannot, as before, display the content of a vector using the standard printing function, which uses format strings similar to those of Python. However, you will notice in the error message that here we actually can do it, but we must use a different kind of display, which is called the debug display, which is specifically intended for debugging. And the reason is, I can explain it later on, but there is no single way that everyone agrees on what would be the proper way to print the contents of a vector in any circumstances. The second problem we have is that we are not allowed to sort floating point data because, remember, not a number is not ordered. If we know that our data does not contain not a number, then we can assert absence of it in various ways. And finally, there is a third issue, which is that here we are dividing by the literal 2.0, and we cannot do that in Rust. And that's more debatable whether that should be an error, but in any case, the error message points to further explanations. Still, there is one remaining issue. Like the C++ code, our Rust code does not correctly handle empty inputs. Unlike in C++, this will not lead to undefined behavior at runtime. It will lead to a deterministic crash using a mechanism known as the panic. We need to ask here whether that's a good thing. I would argue it's a bit of a matter of point of view. If, as the author of the median function, you think that passing in an empty vector is blatantly invalid usage and should not ever, is not something that someone correctly using the library would ever do, then you should spell out in your documentation, this function does not accept empty vectors. If you pass it an empty vector, it will panic. That's fine if you warn people that you would do it. If you consider an empty input to be a valid input, then you can address this in a different way by returning a so-called optional type, which is something that can either contain a value or not contain a value. And then it's up to the caller of the function to check whether the function returned a value or not. This is a good occasion to branch to the next topic, which is the problem of error reporting in C++. Historically, C++ bet everything on the mechanism of exceptions for error reporting, like in Java. But as we learned over many years, there are several problems with exceptions. First problem is that exceptions in terms of performance are quite expensive to throw and to catch on the user side. which means that they are not appropriate in situations where you get an error that's going to happen rather frequently and you want to handle it efficiently. Furthermore, because exceptions trigger stack unwinding, which calls destructors and so on, it's hard to keep code correct in the presence of exceptions. Remember my warning about initialized memory at the beginning of this presentation. And finally, it's common in C++ to use destructors for resource management. But the community consensus is also that you should not you throw exceptions in destructors. The problem is you actually do not have any alternative way provided to destruct objects in a fiable way. So basically, your options are to either ignore error, which is never a good idea, or throw an exception anyway and hope this time it works. What if you are convinced that exceptions are problematic and don't want to use them? Well, then you get the jungle. Everyone took a different approach here. Some projects use a subset of the possible output values of a function to signal error. Like, for example, if you return an integer type, maybe the maximal or the minimal value of this integer type will be used to report error. If your function normally does not return a value, it's a void function in C++ terms, then maybe you are going to do it the C way and make it return signed integer instead, and hope that maybe, hopefully, your users will check that this integer can be negative to signal an error. In practice, no one does that. You could also use exotic return types that are specific to your project, which allow you to carry both a result and an error in a clean way. But each project does it in its own way, which means that in final applications, combining types that can contain error from different libraries is a nightmare. And finally, you get something which is more of a culture issue, which is that C and C++ developers are notoriously bad about documenting the cases in which their functions can error out. So even with exceptions, you can have issue where you get an exception thrown at you that you did not expect because nothing in the documentation says that it can happen. How does Rust address this? For any error that is recoverable, like you went looking for a file on the disk of a computer and you did not find it, or you do not have permission to access it and so on, the recommendation is to use an enumerated type called result. And the idea of the result type is that it can contain either a valid value of a certain type T, a value of another type E, which describes that an error occurred. It tells you what error occurred, what kind of problem happened. And the very important point of the result type in Rust is that you cannot get to the valid output without first specifying what should happen in case there is an error. You can check for possible errors, take various actions. You can say that these errors are actually unrecoverable for you and crash if there is an error, but you must say in your program what happens when there is an error. This is a good policy typically for library that fail typically in recoverable way. But sometimes there are some operations where it's agreed on by the entire community that if a program does this, it's a bug, like accessing an array at an invalid position and so on. And in that case, we are not going to use the result type unless we are in some critical software that must never crash ever. We are instead going to use the panic mechanism that I previously mentioned, which causes typically the program to crash. Actually, it's configurable. You have two main modes of operation. The unwinding panics, which work like C++ exceptions. They try to clean up all program states before crashing, and they give you an option to interrupt the crash at some safe boundary. And in cases where unwinding is too expensive, you have another implementation of panics, which is aborting, which halts the program immediately without any cleanup. Again, you are allowed to catch panics when they are in unwinding mode, but you are not expected to do it frequently. Panics are meant to report program bugs. They are not meant to report usual errors. So you should only do it if, for example, you are doing a web server and you have a pool of threads handling network connection, and you don't want to crash the entire server when one connection does something wrong. And the third point of the Rust error handling strategy is that everyone agrees on it. And there is a strong culture in the Rust community of documenting error cases and telling, this function can fail in this and that way. It will panic in these circumstances. If it does not panic, if it can return error, this is what the various error cases mean, and so on. Another issue in C++ that Rust tried to address is that I mentioned previously that C++ has many flavors of polymorphism. The specific case where you want to have some kind of abstract interface that contains multiple methods, this actually boils down to two options. You can either do dynamic polymorphism using virtual methods and class inheritance, or you can do static compile time polymorphism using templates, concepts, and specialization. The problem is that in C++, these two mechanisms are completely incompatible. They work in completely different way. They use different code constructs. They follow different rules. And so it's very difficult to switch from one of these options to the other. The problem is that sometimes you will need to do so. Maybe you started with dynamic polymorphism, but then you realize that this has too much runtime overhead. Static polymorphism at compile time can allow you to reduce the overhead, but now you need to rewrite in this direction. Similarly, maybe you started using templates, and then you end up with a program that is very hard to compile. It takes a lot of time to compile. The compiler uses an enormous amount of memory, sometimes to the point of crashing your continuous integration system. And then you will need to go from this direction to this direction. And because these two mechanisms are completely incompatible, this is going to be a very painful process. A third issue is that even with these mechanisms, which are the most powerful polymorphism mechanisms in C++, you cannot change the interface of types from external libraries very much. And this can cause interoperability issues when you have different libraries that each implement the same concept in slightly different way using slightly different interfaces. Rust tries to address these issues using a mechanism called traits. The first thing about traits is that they address both static and dynamic polymorphism. You can use them for generic code that knows which type it's dealing with at compile time, and you can also use it with more object-oriented-ish code that does not know which type it's dealing with until runtime. What is a trait? A trait is a set of methods, interface methods that are not associated with data members. If you've ever done some Java, this is like Java interfaces. To this, we add a few other things. A trait can define some associated type, and this allows your trait methods to return values of different types depending on which concrete implementation of the trait you're dealing with. You can have constants, numerical constants, for example. You can provide default implementations of trait methods. If there is a basic way to do something, and then there may be a more optimized way for specific types, you can have this. And both methods from traits, associated types, and the traits themselves, everything can be generic. Which allows things like, overloading the addition operator, defining addition with different number types if you want to. And the way Rust manages to unify static and dynamic polymorphism is by defining a dynamic subset of the traits. That is to say, you can always use a trait for specifying the interface of your generic compile time code. If you want to use it at runtime, then you must follow some extra constraints. Finally, Rust traits have one last capability, which is a superpower in practice, which is that you are allowed to implement a trait from types from different libraries, including the standard library, for example. And this is enormously useful when you want to have abstractions that interoperate with code written by different people. Let me give you an example by implementing simple AX plus Y in Rust. So normally in Rust, you have iterators that allow you to do this. You will learn more about them in my next presentation in a few weeks, months. And you would iterate over a collection. You would zip another collection to get an iterator of pairs from both collections. Then you would transform the pairs into the result, AX plus Y. And finally, you would collect the result into a new collection, a vector. And there is a library called Rayon, which allows you to do data parallelism like TBB in C++. And the way it works is that instead of calling iter here or into iter, you just call into parallel iterator. And you're done. Your code is running in parallel. Let's contrast this with the standard execution parallel policy in C++ that Pierre introduced last time. First of all, this is a third-party library. The into par iter is defined by a trait within Rayon. We did not need to change the standard library to make parallelism work. So the standard library can stay simpler. It doesn't need to tackle as many tasks, which means that it will be more reliable, better maintained. And we don't need to get some weird abstraction breakage. Like as Pierre mentioned last time, when you used std execution par in C++, suddenly your program needs to link to TBB. It's a bit weird that something very fundamental like a compiler depends on a high-level library like Intel threading building block. The syntax is also much less verbose than when using std algorithms. And it enables new things like, collecting into new vectors. And it's more scalable. You can do more complex pipelines. It's so much better. Now your project grows, and at some point you will always need to do some code generation. It's this sort of thing that everyone agrees that it's a pain, but you end up having to do it anyway someday. In C++, the way this is typically done is using template metaprogramming, which, if you ask me, is based on a compiler bug that accidentally became a language feature. The result of using this counterintuitive construct, which is about the compiler not sending an error when you call a method with an invalid type, is that you will get some weird code that only experts can read, which is very hard to maintain. And you will also make your compiler do very stupid things like instantiating structs that only serve to generate code and that do not actually are used to store data as a struct normally is about. And this is all very inefficient. So your build is going to become slow, consume a lot of RAM. You will get problems in CI and so on. Let's say you don't like template metaprogramming like me. What alternative do you have? You have preprocessor macros, but these are very hard to use and at the same time highly underpowered. There are very few things you can do with them. You can do very nasty thing like using compiler-specific debugging function to get a string representation of types and then parse this representation to deduce a memory layout of type, this sort of horror, which is obviously very non-portable and very likely to end badly when the compiler is updated. Or you can give up and add a third-party program to your build system, like root those. But this comes with all kinds of other issues because now we need to deal with C++ build systems, which are a pain in their own. In Rust, we have better options at our disposal. We have traits and generics, they can already serve to do the same kind of tricks that we would do with C++ templates in many circumstances. They are a bit more limited because we do not have yet a specialization mechanism that is as general as that of C++. We have build scripts, which lets you execute arbitrary Rust code during the build of a library. And this is convenient when you need to link to some C library, for example, and then you need to find it using tools like pkgconfig. And finally, we have lexical macros. By lexical, I mean that unlike the preprocessor macros of C and C++, these macros do not copy and paste code without knowing what it is about. They operate on what's called token trees, which is a bit like the abstract syntax tree at the inside of a compiler. And this means that the macros of Rust have much better ergonomics and much better expressivity than C and C++ preprocessor macros. They can do a lot more things and they are easier to write. Let me give you an example. So let's say I have a struct in my program with some members. And now I want to turn this struct to JSON or Python pickle or whatever. Well, all I need to do is to get a library called serde and get the deserialize and serialize macros from it. Then I put an annotation called derive serialize deserialize, and it will automatically implement traits called serialize and deserialize, which then let you turn your data of type record into JSON, CSV, pickle, whatever you want. Again, because of how powerful the Rust macros are, this doesn't need to be in the standard library, which means that we save an enormous amount of time. We don't need to face the committee for every minor thing. The language is powerful enough that the third-party library ecosystem can do a lot. And this is not limited to serde, actually. Like in the standard library, for example, you have another macro called debug, which lets you automatically generate the debug output that I mentioned earlier, which lets you do printf debugging with custom struct at very little cost. Let's talk about building code now. So in C and C++, when you need to actually build your project, and it's not a project that's simple enough that you can just call the gcc myprogram.cpp and be done with that, the typical option is to use CMake. Now, CMake is a contender for one of the worst pieces of software on the face of the earth. It's horribly written. It's not documented in any capacity except for reference documentation. And its internal semantics is executing scripts which are morally equivalent to bash scripts in Unix systems, but again, without the documentation that comes with bash. So my opinion about CMake is that if you don't hate CMake yet, you've not dealt with it enough. You've not yet written enough CMake code, CMake modules for your libraries and so on. And the consequence of having such a terrible build system is that people will be very wary of reusing code, especially when you combine it with another problem on Linux, which is that we have many different Linux distributions, each packaging libraries in a different way with different names, different versions, and so on. And because reusing code from other people is so hard, people in the C and C++ community tend to be very averse about using external libraries and to instead write their own code for the same task over and over again, which slows down development and leads to worse quality code. The answer of Rust to this is to include in the standard toolchain a tool called Cargo, which serves a dual purpose. It's both a build system and a package manager for third-party libraries, third-party Rust libraries. And it's very easy to use for small projects, yet it can scale to relatively complicated projects. Like there is, for example, a web browser called Servo that's built still using Cargo. Cargo makes it very easy to depend on third-party library, which can be, depending on who you ask, a good or a bad thing. But in any case, it leads to a very lively third-party library ecosystem, of which I've shown a few examples earlier. We get close to the end of the presentation. One last issue with C++ is that it's lost in its past, by which I mean several things. First, we need to talk about C++ programmers. Most C++ programmers actually do not know what's inside of the latest standard revisions, what was introduced by C++ 11, 14, 17, 20. Worse yet, because C++ is less and less taught in universities, and when it's taught, it's usually from very old courses that are only kept due to inertia. This means that even young C++ practitioners do not get trained using the latest standard revision. They keep using practices that the C++ community has generally agreed at large to be bad and to be avoided. If you do want to use newer standard revision, then you will hit a second issue, which is that C++ compilers do not keep up with the new standard revisions either. You get Linux distributions like Red Hat Enterprise that take pride on distributing very old compilers that do not support modern C++. You get embedded systems that use some compilers that are basically unmaintained and certainly will never get support for newer standard revisions. And beyond that, the language itself is accumulating bit rot over time. You have many bad decisions from the past of C and C++ that keep influencing new decisions made about the evolution of the C++ standard. Things like the copy and paste preprocessor and the include mechanism, which people try to fix with modules, but they manage to produce a design which is worse. I can get into details if you want. You get ill-defined primitive types, which means that when you get an integer of type long, you have no idea if it's a 32-bit or 64-bit integer, which will cause portability problems. When you get an integer of type char, you do not know if it's signed or unsigned, which can be a problem if you're manipulating bytes. If you are using literals in your code, and obviously you are, because who doesn't have number in their code, then you will realize that because literals are typed in C and this carried over to C++, you need sometimes to use stupid suffixes just to say, I want to use a 64-bit integer, I want to use a single precision floating point number, which quickly gets insane and can be a source of performance and correctness issues. Many constructs in C++ have wrong defaults, switch falls through by default, assignment copies by default, const is something that is opt-in rather than opt-out. Many implicit conversions are defined, not all of them are wise. Vector bool is a mess, and numeric limits mean as well. How does Rust address this? By showing C++ the way it's done. If you look at C++ 17 from the perspective of someone who used the very first stable version of Rust, which was published 2 years earlier, much of C++ 17 is about catching up with stuff that already existed in Rust in 2015. And some of them try to catch up, but are very broken. Like std optional is much more difficult to use than option in Rust. Std tuple is almost impossible to use by non-experts. Structure binding are only half of what they should have been. They only work in very specific edge cases. Class template argument deduction. I believe if you conducted the poll with C++ practitioners, you get less than 1% of people even knowing that it exists. And std variant is also an absolute mess. Surely the C++ committee must be learning and doing better, however. Well, yes. If you look at C++ 20, you have more good copies from Rust. Many of the C++ 20 features are actually backports from stuff that Rust had, again, for many years before. But still, you still have some stuff that doesn't work, like ranges have terrible performance, as Pierre mentioned. Coroutines are almost impossible to use and yet manage to slip in mandatory memory allocations in a language that's about avoiding it normally. Modules are broken. They require you to run the equivalent of a web server just for your compiler to find out in which source file a module is declared, which is insane. Concepts, as we've seen, are broken as well. And because of all of these reasons, I believe that if you start a C++ project in 2024 or 2025 for that matter, there are only two good reasons to do so. Either your code is meant to be part of a larger C++ project, and I do not encourage people to be working code in a different language. Or your code is tackling a problem space where you have more mature libraries and tooling in C++. This can happen especially in the space of GPU, as we are going to see in the next presentation. In any other situation, I believe you should consider using Rust instead. The language is now mature enough that it will rarely be the limiting factor in your development. The ergonomics are infinitely superior, as I hope this presentation convinced you. So you will get less bug, and thus you get more time to implement cool features and performance optimizations. And paradoxically, because of how bad the C++ learning resources are, it's actually easier to find learning resources and ecosystem support for modern versions of Rust than it is to get a toolchain that and tutorials that correctly support modern C++. So that's it for today's presentation. Today you saw why Rust can be a good choice for numerics. And then next time in May, you're going to see how you can write Rust numerical computations in practice using many calculation examples of increasing computation complexity, going from basic loops and iterators all the way to SIMD, parallelism, GPU, and so on. And along the way, I will also introduce many gems from the library ecosystem that, as you will see, will also save you from much tedium of writing numerical application. Thanks for your attention, and now it's time for questions.
Okay, thank you, Hadrien. Maybe just to, before going to the question, you mentioned that if you have a big code base in C++, maybe you want to keep it and not go in Rust. But on the contrary, as Sebastian said, if you have a project you already know and you have a lot of unit tests in it, it could be a nice way to try Rust and see what's going on in this language. So it forces you to redevelop and to redesign your software in a good way. So it could be also a nice point to take.
Again, my point is I don't like gratuitous rewrites. If people have already decided that they have to rewrite some code because it has become unmaintainable, then yes, they could try rewriting it in Rust as well as in modern C++. For me, yeah, I would argue that in this case, Rust can make sense unless you need to bind with lots of other C++ code, which is currently a bit difficult.
Yeah. If you depend on a lot of other library, it could be difficult. But if you have a nice defining set of
if it's well
library,
decoupled or if it's
normally you could give it a try just to see, or maybe a little part just to practice a bit on something that you can use later. Question from Tambet, how the traits are different from Java interfaces or even abstract classes in C++?
You can use it for compile time polymorphism as well as for runtime polymorphism, which means that if you are doing generic code, if you are rewriting, for example, the standard vector class, you could use traits to define its interface. This you cannot do in C++. In C++, in general, there are many limitations of what you can do with abstract classes. They cannot have templated methods. They require you to use the objects to access it via a pointer, which means that everything in a typical program needs to be allocated on the heap, which can cause lots of memory allocation, which is a performance problem, as we saw last time. So yeah, from this perspective, you can think of them as combining the best of the C++ concepts and C++ abstract classes.
Okay, a question from Mark. How is the constraint generic traits system differs from the include system in C++?
So the include system in C++ allows you to bring source files in scope, like get a library and so on. You cannot use includes to define something like a standard library collection. You cannot define std unordered map using includes, for example. For this, you need to have a construct which is understood by the compiler and not just the preprocessor.
Okay, a question from Michael. For C++, we have a single sources heterogeneous programming model like Coco, Sycl implementation, Hadrien, and so on. What are some possible solutions to archive this in Rust?
So as I mentioned, GPU is one example of a situation where C++ is quite a bit ahead, honestly. But in the next presentation in May, I will present a few technologies that you can use. If you just want some names to look up for now, there is a project called, it's a misspelling of kernel called KRNL, as you see in the chat, which starts giving you a CUDA-like feeling in Rust based on Vulkan under the hood. It's a bit young. I want to try it out before recommending it more. There is something called kubecl, which is about translating your Rust to some intermediate representation, which is then itself translated to PTX, SPIRV, and so on. And there is also work in progress support for LLVM offloading in the Rust compiler. This is very, very young. I don't know if this will be ready in time for the school. Right now, you need to use a fork of the compiler to use it. But the idea is to use the infrastructure that is already in place, for things like OpenMP4. So this would allow you to use stuff like CUDA and AMD ROCm ecosystem using code annotations directly supported by the compiler backend.
Yeah, and I think you did not mention that, but also, Rust C is based on LLVM, so you can get all the stuff, SPIRV stuff that you can use with compute. So in C++, you can get the same in Rust also.
You can get it, but right now it's, there is some plumbing
work to do.
It's a bit young. There is some plumbing work to do to make it usable, and this plumbing work is still very much work in progress. So there are a bunch of these projects. I want to try them out this year and give you some report in the next webinar at the school of which one you should or should not use and why.
Okay, so from Moran, thank you for the very interesting presentation. From Valentin, thank you for the presentation. I did not get how you solved the divide by 2 error in your first example.
So there is another one first, maybe. Why would you say that Julia isn't suitable for larger projects? So the problem with Julia is they do not take software engineering seriously. They do not have hierarchized module system by design, which means that you get namespace conflicts all the time. They have a weak type system that does not let you specify in your interface what kind of data you accept, which will lead to problems later on when people pass in the wrong type to your function and it tries to duck type it into something and it either produces a bad result or crashes. In general, Julia feels like, MATLAB programmers trying to make a modern successor of their language, but not something that you would want to use for a larger software project where structure and type checking become important stuff. So now I can handle the divide by 0 to error. So this one is actually a bit of a tricky one. Currently in Rust, as in C++, you cannot have custom, you cannot reuse the literals of the compiler, like the numbers you type in your program, for your own types. And this means that support for number in general is a bit tricky. What you can do is you can say my floating point type must be convertible from, say, like single precision floating point numbers. This is true of both single precision and double precision numbers. And then once you add this constraint to your generic code, then you can say, instead of typing 2.0 divided by 2.0 in your code, you can just say divided by t from 2.0. That's one way. Another way is to use the numtrace crate, which allows you to get the one constant, and then by doing 1 plus 1, you can get the 2 denominator, but that's a bit cheating. I personally prefer adding a constraint that requests the conversion from single precision numbers, because this conversion is almost always there, so that's not a big limitation.
Okay, from Moran, I just worried about one thing. In C++ exceptions, allow basically assume that the result in a call is valid, and if is not, propagate the error in higher in the call stack, where I can deal with it and decide whether it's critical or not, but maybe I'm not using the exception very well. The result T, template T and E approach in Rust seems to be very verbose. Will I end up checking that every call return a valid result? If so, I probably end up using the panic unwinding mechanism, which isn't recommended.
So
yeah.
If you asked me this question in 2015, when there was the first stable release of Rust, I could have been sympathetic to your viewpoint. Since then, however, there have been many innovations in the Rust library ecosystem and standard library and language, which give you many different shortcuts which allow you to propagate errors in the way you suggest quite easily. And these days, it's not really that much of a problem anymore. We can discuss this more at the school, maybe, because I don't think I will cover it that much, but yeah, it's possible to write code that explicitly tells you where it's propagating errors, but with a single concise sign, which is a question mark. And this, I believe, is an okay trade-off. And it's good to know, just looking at the code, what kind of function inside of the code what kind of line of code can throw errors. So I think it's a good property to have.
Okay, another question from Anton. Is Rust standardized enough in order to guarantee that the program written now will not break down with future compilers?
Basically, yes.
Yeah. Okay, from Valentin, is T from 2 kind of the same as a static cast in C++? Not really, but a bit?
Yeah, kind of.
Yeah, at least, in your C++ example, you can cast your 2 with the cast operator.
I would say, to my mind, it would be more similar to this, but yeah.
Yeah, maybe you just cast operator and not a static cast call.
Because I'm not sure if you can overload static cast for your own type, but maybe yes, it will call the explicit constructors. I don't remember that one.
Yeah, for the divide by 2, you can definitely use T in parentheses, and then you have your cast, and that's it. No problem. From Mosa, comment on the divide by 2 in Rust, the literal isn't type.
Yes, which is a good thing.
Yeah, that's a good thing. So it won't be float 42 or float 64 unless that decision can match a parent. Okay.
That being said, I do not agree with this comment. Actually, you could enforce literal typing using this sort of construct. It would not solve the problem, however, which is that you never say that T is dividable by a single precision floating point number.
Yeah. Yeah, that's kind of the same in C or in C++. You don't use 2.0 but 2.0f for floating points.
Yeah, and in generic code, what do you do?
Yeah, in generic code, it's a bit annoying, but you can cast dynamically the value. But again, you will have a stupid cast inside your your code then. But okay, you can live with that. From Michael, when will registration for the school open? Oh, it's a good question. Normally,
we already have pre-registration, I believe.
You have pre-registration already, normally end of this week or beginning of the next week, because we are a bit short, but normally it should be maybe tomorrow or Monday, next Monday, something like that. Okay, from Thomas, what about Rust and MPI plus OpenMP? Again, MPI plus OpenMP.
Yeah.
I consider these two to be standard paradigms for CPU distributed and shared memory computing in HPC. Yeah, a lot of stuff that we already mentioned. Does Rust work with them or provide competitive alternatives?
So the answer will actually be a bit different for the two, so I will split them. For MPI, you have bindings that you can use, and I have seen some people write distributed applications with them, and they seem happy about it. So it seems that part is okay. For OpenMP, it depends on which OpenMP you are talking about. In the mind of many people, OpenMP is about thread parallelism on CPU, which is until OpenMP 3, it was I believe, the only thing that OpenMP could do. This, you don't actually specifically need OpenMP to do it. You know, thread parallelism, it's inside of your application. You don't need support from the underlying operating system, so you can do it however you like. Personally, I would recommend Rayon for doing this in Rust, because as you've seen, it's quite powerful. If you're talking now about OpenMP for GPU, this, as I mentioned, is a work in progress, which I hope maybe we'll have some first version in the Rust compiler in time for the school, but it's not sure. It may be for next year.
Okay.
And then until you get that, you have kernel, kubectl, or directly writing Vulkan code, but that's a bit different.
Okay, so thanks, answer for the very lengthy question from Juan. So thanks from Valentin. Okay, so if you don't have any question, I can just have for mine. Yeah, you talked at the very beginning of your presentation. Yeah, we have, with this wonderful C stuff with a lot of problem, we have a nice ecosystem with Hadrien, with GDB, with Macau, with a lot of tools to do all this stuff. So it's a kind of a good point. It's not such a good language as you mentioned, because we can have a lot of trouble with it, but since we have
it's certainly the case that tooling to some degree can compensate.
Yeah.
However, I would argue that the static analysis tooling in C and C++ is not very good. We have very good dynamic analysis tooling. Yeah. The problem with dynamic analysis is that you need to have tests that trigger the right configuration for the bug to manifest, and this can be tricky.
Yeah, this is tricky. So more seriously, do you have an example of things you must implement in unsafe mode in Rust that you cannot
well,
normally?
If you are writing, say, an operating system and you need to interface with hardware, then you are obviously doing things with memory that the compiler cannot check is correct. If you are binding to a C or C++ library, you are effectively executing arbitrary code that can do arbitrary things with memory. So again, the compiler cannot prove the safety at compile time. So here too, you will need unsafe.
Yeah, that's an interface problem. Okay. But even for the memory, if you allocate your memory, you don't mess up with it, and you access it nicely.
Well,
Normally,
this you can do with standard collections like
it should be okay.
vec and so on. You rarely need to call directly into the system memory allocator.
Okay, on your function, it's really strange to talk about this median function. And the first thing I will do with this function is to check if the vector is empty or not. But
yeah, but mistakes happen. I know
mistakes happen.
I
Yeah,
make
but
this one all the time.
but yeah, that you mentioned at the very beginning. Both Rust and C++ are difficult to learn, and you have to get used to, and to have the good reflexes to when you program. And even if the language is better to find the problem, you still have to do correct stuff at the end.
I mean,
Yeah.
the compiler will never, no compiler can prevent you from writing a function that says it returns 5 and returns 2.2.
Yeah.
You will always need tests. The point of having all this static analysis is that you will need less tests and they will fail less often.
Yeah, speaking of tests, you didn't present the test suite of Rust.
Yes, because this presentation was already 1 hour, and I thought
yeah, or maybe for the school,
but,
you will have time in the school.
There will be a section, I think. Maybe I don't have one yet, but I can totally add one.
Yeah.
I have one in the
really
next webinar.
Also.
This one I'm sure about. I don't know if I present it at the school, but I can add something.
It's nice also with the next webinar, but for the school, it could be a nice point also, because we will all speak about tests in the school. So for my lecture, for your lecture, for the lecture of Sébastien, so it's important to have things nicely done. Oh yeah, another point. Presenting root to highlight how bad you can go in C++ project is really not fair, even if I agree with you.
Well, I mean, it could be root, it could be any code generator, but in general, integrating external code generator into your build is a bit of a pain.
Yeah, this is the worst one. And yeah, you're also right. Yeah, C++ is quite lost in its past, and for the very old lectures, it's kind of difficult to upgrade. And I think you did not mention also that I will mention, because it's my problem also. The documentation of C++ in C++ reference is horrible. And once you want to learn C++ 20 by that, it's really painful.
I mean, the problem is, as in many projects, we have pretty good reference documentation if you already know what people are talking about, but we don't have tutorials, because writing tutorials is a special skill that few people have in the computing community, and that's in particular, we don't have many good tutorial writers in the C++ community, and that's a problem.
Yeah, that's a big problem. Yeah, you mentioned also Rail for the horrible and painful for the developer, because we use compiler which are, in the best case, 10 or 15 years old, which is quite stupid stuff, really stupid in this point. And if you disagree with that, you can check Csmith if you think that G++4 is stable because it's old. Because I don't want to get upset with that right now, but yeah, that's stupid stuff. You have to deal with that. And you can also, in fact, we use containers to avoid that, to have a nice deliverable. It's not always possible, but and it's not really simple also to use containers, but yeah, that's the problem. But I'm not sure if it's for everyone, because we are both in particle physics and in astrophysics, so of course we have to deal with this.
I think that's a common problem for
other people.
Enterprise systems also, to have this sort of distributions.
Yeah, but if you have I don't know, Kubernetes with a recent kernel, stuff like that,
it
you don't
depends.
have this
Yeah,
problem.
if you can afford to use a container, you can use it to work around this. I agree.
Yeah.
Sometimes, however, containers cause other problems, like they are very heavy in terms of memory and downloads, which can easily get resource intensive, that sort of stuff.
Yeah. Okay, question from Hughes. Maybe a last question about memory management. Is it possible to implement an insertion sort on a vector of pointer in Rust without unsafe or not doing deep copy? I did not manage to do that.
You have swap. I believe you could use that. I mean, if it's in a vector, then you will need to use a method of the slice type. which is called, I don't remember how, but I will just get it. And it has swipe in the name. And then when you use that, you can use it to swap elements. And once you can swap elements, you can implement any sort you want.
And it's the same in C++. You say, okay, I implement my operator, and that's it. If you want to use maps, or if you want to use sort or stuff like that.
Well, here it's a bit different because one limitation annoying of the borrow checker in Rust currently is that you cannot have a reference to two different elements of an array at the same time. That's really annoying. And so there are many methods on the slice type, which is the equivalent of stdspan in C++, which allow you to do this sort of stuff. Oh, yeah, insert. You also have insert if you want.
Yeah, you have insert also if you want.
That's not on slice, however, because it changes the size of the container, so it will be on vec. But yeah, you have it.
And do you have the equivalent of ranges in Rust? So to have a range of number, but without the allocation, only the boundaries?
Well, basically, what Rust calls iterator, the things that Rust calls iterators, C++ people call them ranges.
Ah, okay. You don't get that
Rust
point.
doesn't have an equivalent of the C++ iterator that does not know when the end is, because that's basically
that's a big
undefined
problem.
behavior waiting to happen. So that's the spirit.
That's a big problem. Yeah, so it's hidden under the hood of the iterator first. Okay. So I think that's it. If you have a last question or you want some pointers maybe on the documentation or stuff like that, I see Hadrien did also already that in the chat.
If you want a generic Rust course, I can give you one. But if you want a numerical Rust course, I mean that's the spirit of the school. So
yes,
you will get the best one in end of June, beginning of July.
Okay, so if nobody has more questions, we can end the webinar right now. So thank you everyone for joining us today. So exceptionally, next week we will not have a webinar because it's GTC and I want to sleep. So it will be for the next week. We will have GPU architectures, how to program them, what all the magic inside it. So as Hadrien did for the CPU, I will do the same for the GPU. And so it will be in 2 weeks from now, because next week it's GTC. And if you want to have a look to the GTC, you can also have a look if you want. And we'll give the summary of the GTC of next week, the 12th of June, so just before the school, if you want to wait for this summary. And yeah, have a good day and see you in 2 weeks, exceptionally. Bye.